In this video, we're going to look at power functions. A power function is basically any single-termed expression that has a variable as the base of an exponent. It can be written in the form f of x or y equals k times x to the a. A, your exponent, is referred to as the power, and k is called your constant of variation. We would read that expression and say f of x varies as the 8th power of x. So that equals k we read as the word varies. The graph of a power function is going to depend on what your exponent is. If that exponent is a positive integer, then we would refer to that as a monomial because it's a polynomial of a single term, so monomial. If the power is a positive integer, then we would call that a direct variation. If the power is a negative integer, then we would call that an inverse variation. So here we're going to take a look at some power functions, and we want to be able to determine the power, whether it's direct or inverse variation, and what the constant of variation is. So looking at this first example, my power is going to be 2. So we would say that that is direct variation, and then my constant of variation is the pi. In the next example, I'm going to rewrite this as 5/3 x to the negative 4. So when you're pulling the power, you need to make sure that it's written in the term, or in the form y equals k times x to the exponent. So my power is going to be negative 4, which makes this inverse variation. And then my constant of variation is the 5/3. In the next example, we're going to say that my power is the negative 2, so inverse variation, and my constant of variation is k. In the next example, the circumference formula equals 2 pi r. There's no exponents, so we're going to say the power is 1. So this is direct variation. And then my constant of variation is the 2 pi. So your constant of variation is everything except for the base and the exponent. And in our last example, my power is going to be 3, which will be direct variation since it's positive, and my constant of variation is going to be 4/3 pi. So taking a look at the graphs of the power functions, remember we mentioned that the graph is going to change depending upon your exponent. So you want to be able to sort of look at a graph and identify what the exponent would be, or if I give you an equation, you want to be able to tell me in general what that graph is going to look like. So we've got some examples here, so sort of moving across here from left to right. The first one is when a is a positive even integer, so something like x cubed or x to the 4th, then you're going to get that parabola shape or that U-shaped, and your domain is going to be all real numbers, and your range is going to be 0 to infinity with no transformation. Moving over to the second one, when a is negative and an even integer, so this is y equals x to the negative 2 or 1 over x squared. So remember, we can write them either way. This is going to look like that inverse square function from your basic functions. So you have the corner shape in the first and second quadrants, and you have asymptotes on both axes. So your domain is all numbers but 0, and your range is everything above 0, not including 0, because remember, that's your asymptote. Then we're going to look at when a is an odd integer. So first, if it's positive, it's going to look like the cubic function. Your domain and range are all real numbers. Next, if it's an odd negative integer, or if it's in the denominator, remember, then you're going to get that inverse function. So you're going to have that corner shape in the first and third quadrant, and again, asymptotes on both axes. And then the last one, we're restricting the domain. So pay attention here. We're choosing to restrict the domain to be only the numbers from 0 to infinity. If we don't restrict the domain, then there's a lot of different variations of what happens on the left side of the graph. But if we restrict the domain, then all of the graphs will look similar. So when our exponent is between 0 and 1, it's going to look like the square root function. So since we're restricting the domain from 0 to infinity, the range will then also be from 0 to infinity. So again, what you'll need to be able to do here is sort of match graphs with equations in a matching section or multiple choice, something like that. All right, next we want to look at some modeling with power functions. So first we're just going to look at doing power regression on your calculator. So we're going to put that data into the calculator. So remember, stat edit, and get the data in your list 1 and list 2. This question asks us to obtain a power function model. So then we're going to go stat calc, and we're going to go to power regression, which is down, I believe it's A. So we're going to choose power regression. Again, X list is L1, Y list is L2. You can leave frequency list and regression equation storing blank, and then just go ahead and calculate that. So using the calculator output, we can then write the equation. So using our power regression output, we can write the equation. So this is going to be y equals 0.2 x to the, and then I'm just going to use 1.5. I'm just going to round that to 1.5. And then this question asks us to do a prediction using 4,497. So y equals 0.2, 4,497 to the 1.5, and we get about 60,313 days. Looking at a couple more modeling problems. These are going to be some word problems. We're just going to practice kind of looking through these and finding the information that we need. So this one, from empirical evidence and laws of physics, it has been found that the period of time t, so there's a variable that's going to be important, for the full swing of a pendulum varies directly, so those are important keywords, and then as the square root of the pendulum's length. So when you're reading through the problem, you want to look for two different variables. You want to look for the words varies or is proportional to, and then any other like math words that show up. So this continues, provided that the swing is small relative to the length of the pendulum. So all the other words in that first sentence really we don't need. Then it says the time for a swing with pendulum 10 feet long is 1.2 seconds. So we want to do two things here. We want to express this relationship as a power function. So if we kind of go back through that sentence where we found the key information, so t varies directly, so equals k. Since it varies directly, we know that the variable is going to have a positive exponent or definitely be in the numerator. So we're going to do the next variable is L, and it's the square root of L, so we can write it like this, or if you prefer, we can write this KL to the 1/2. Now what we want to do here is plug in the values that we were given in the problem so that we can find what the value of K should be. So we're going to plug in, so a pendulum 10 feet long has a period of 1.2 seconds. So I'm going to go 1.2 equals k times 10 to the 1/2 power, or you could leave it with the square root. So then just solving for k, we're going to get 1.2 divided by 10 to the 1/2 power, and we get about 0.38. So k equals 0.38. So then my answer here is going to look like t equals 0.38 square root of L. So then when we come over to part B here, find the time for a swing with a pendulum 3 feet long. So time equals 0.38, and then we're just going to do the square root of 3. We get about 0.66. So one more example here with the power functions. So the volume, so again, there's my variable. So I got one variable, volume of an enclosed gas at constant temperatures varies inversely as the pressure. So if we use that information to write our relationship as a power function, so volume varies inversely. So remember that's going to equal K divided by the pressure. So I'm just going to use P for pressure. There's no indication of a power there, so we're going to assume that it's just power 1. Again, now we're going to use the second piece of information. A pressure of 3.46 liters is 0.926. So when my volume is 3.46, my pressure is 0.926. So again, we're just going to solve that for K. We'll get K equals about 3.2. So then my equation, volume equals 3.2 over pressure. So then coming over here to part B, find the volume if the pressure is 1.145. So volume is 3.2 divided by 1.452. That volume is about 2.2 liters.